Okay. Looks like it's on live on the YouTube. Yeah.
Okay.
Looks like it's on live on the YouTube. Yeah.
Okay.
Looks like it's on live on the YouTube.
Okay.
Hi. Good evening, all. Thank you very much for joining in. It's always a privilege to host you on the sessions which we've been putting it across in the past and also for now. So we shall start the session in a few minutes. We're expecting to have a lot of people joining in from over the all over the places, even India and a few other places from US and Europe. So I think before we join the session, we will have a bit of a privileged time to discuss and know about each other, and also to know what kind of what brings you here, what motivates you to be a part of this session today. So kindly introduce a bit about yourself, and tell us what really interests you, and what really motivates you to take part in this course today, which we're going to deliver. So do use your chat box right there on the live chatting. So just drop your details. So let's everybody know each other. So waiting for your answers. Please go ahead. So we get to see that there are already few participants from our past programs. Thanks everyone for joining back. So thanks for joining in and giving a bit about yourself, Salil. So Ajay, Shaji, Anirudh from Pune. That's good to know. Please do introduce yourself, everyone, and also just let us know, what interests you to take part in the program here, so that it gives us a direction to put our discussions into an alignment, so that we can make best out of these 2 hours of the session. Priyal from Mumbai, Omkar from Pune. Interesting, Kaushik. E-mobility is my area of interest, and lithium-ion and BMS being a critical part of it is what I brought me to enroll in this course. Very interesting. Ajay, BTech in Electrical and Electronics. Great. Awesome. Ashutosh. That's good to know, Ashutosh. You're part of electric car team. So we should be starting our session in a few minutes. Before we go ahead, just like waiting for a few more people to join Kudos to begin the session. Maheshwar from Hyderabad, Shruti from Pune, Adit from Mysore, Raghuswamy from Hyderabad. Awesome. That's good to have a crowd from various places. Maybe you can also just drop us, which department of studies you're from. Mm-hmm. Jaideep from Gujarat. Awesome. I was captain of team, participated in EBA. That's good to know, Ashutosh. Vinayak from Mumbai will be discussing in thermal. Um, it's a very specific topic. I would touch base on that, but it would be like a half a day session to deliver on thermal management. So we would try to see how much we can touch base and go through that. We could try to see some references and understanding how actually the thermals could affect the battery. But talking in depth about it itself is like a half a day session. Vinayak, we'll see how much we can touch base. Awesome. So Hinder from Punjab. Awesome. So keen interest in electric vehicles, especially batteries and BMS. Awesome. That's really good. I think good to know. We clocked 5:30, and we should be starting the session right away without spending much time here. So definitely good to know. And a few more people here. Rakesh, mechanical engineering. Would learn about maximum continuous current drawn and how BMS would take into an account for a health of the battery in the case. Um, okay, that's sort of yeah. We'll see how much we can touch base, Mir. Yeah, Ravi Teja from Hyderabad. Okay, um, awesome. That's good to know. People from a lot of places. I think we'll get started with the session, and then we'll take ahead. You guys have joined on time, and really appreciate that. So let's get started with the session here and take it high. By the way, good evening, everyone. Warm welcome to all of you who have joined here on the session today. It's a privilege always for us to share our knowledge in the area of electric mobility with our past experiences working with various projects with OEMs, with startups, and also with a lot of student racing teams. It's always good to know and interact with various prospects of the engineering you're from. We'll see how much we can touch base today to cover up in the areas of the powertrain. Yeah. So the whole focus of today's session would be to discuss about a simulation perspective for a lithium-ion cell and the BMS, and in doing that, we'll also slightly demonstrate on the MATLAB model we have been developed in collaboration with a couple of racing teams. So let's go ahead and pick up the sessions here. A bit about myself, who's presenting for today's session. I'm Suraj. I'm the co-founder and CEO at Decibels Lab. I'm the one of the person who will be the course director for all the courses on electric vehicle powertrain systems. Um, a bit of introduction in the background is I'm a mechanical engineer, 2012 in graduation. So I worked with a few of the companies like HP and Fisher Dynamics and Fiat Chrysler and Hewlett Packard. I was a part of the team at ITC Infotech. Through that, I had a chance to work with projects for Mercedes and was working in the US for a while on projects with Chrysler. I like teaching, so that's a bit about myself. And we've been engaged from last close to so 2.5 years in sharing our knowledge and skills. That's my email address. If something is there, you can always reach me out, and we can discuss it for any of the discussions. A bit about Decibels. I'll not take much time here, so that you just know whom you're interacting with. That's the reason. Definitely will not spend much time here, just for a minute and a half, possibly. But about Decibels, Decibels have four verticals of business. One of the business, which is major business for us, is consulting. Consulting in electric vehicle powertrain. We work with few of the startups in India and also some of the startups in Europe and other part of Sweden. We consult few of the startups. And the other areas of, apart from powertrains, we also support few of the areas in new product development and also in the manufacturing sector. We have close around a team of 15 people and plus close around 20 plus consultants across the globe to help us to engage in various activities with all the customers we have. Apart from consulting, so we set up certain labs for research and development, and also the labs for the activities such as testing of batteries and testing of the motors and things like that. Then the third division, because we have all the knowledge about powertrain, working with a lot of customers, and which are OEMs and startups. We have enabled a learning management system, that's the LMS.Decibels Lab, through which you have been participating for all the courses. That's where we bring all our expertise, all our experts into the place and share our knowledge through our courses, which Decibels has been hosting it across. We have reached close to 5,000 students for today in sharing our knowledge in the last nearly 2.5 months. Because we do all of this in consulting and other areas of research and development, and also in the areas of education. So we connected with a lot of industries on the one side, and we connected with a lot of students on the other side, learners, I would say, on the other side. So when industry asks for certain employment opportunities, it means like they want to hire somebody. So we support in hiring some of the candidates for the industries. So let's go ahead in discussing technically on what is going to be the today's session itself. As such, in today's course flow, I would have two things, which is majorly on the cell side, and the second one would be on the battery management system itself. So on the cell side, the very important thing is to understand why we actually model the cell, and also we would understand about how cell is very much non-linear in nature. I would take you through certain understanding of these non-linearities, and then we would get through how actually we approach to model this non-linear system. Then we would have a Q&A session for a while, and then on the other side, with the second part of the discussion, so we'll take a small break there, like a 10 minutes break. So it's always said that human brains have 45 minutes to 50 minutes of concentration capability. So we'll just take a small break there. We'll just take some fresh air and take a sip of water, and we'll just join back in 10 minutes. You can drop in a few questions in between so that you could talk over there. Then after that, we'll discuss more about functionality of a BMS. As such, a functionality of a BMS, there is a lot of things what BMS does. As such, to cover this course on a BMS itself, we have extensive week-long courses, or 2-week-long courses on the BMSs. So we'll talk about one of the functionality, that would be voltage protection as such, and also I'll run you through a few more things and what kind of logic algorithms we approach to build to ensure the protection for the cell itself. So on the BMS functionality side, and then we'll also run through the approach of developing these algorithms, how we actually develop the algorithms itself. And I'll run you through a model-based code generation approaches. Actually, nowadays, nobody sits and writes 1,000 lines of codes into the controller. So you could build a model and tools like Scilab or a MATLAB or a few other tools. We can just export all of that into a C code, and that just works on the controllers. Definitely, there is a limitation on what number of controllers it supports to. The MATLAB has a tool called MATLAB Embed, the Embed Coder. So, and also Scilab has X2C. We would use those PowerTool tools to write those codes. And I'll just run you through the whole industry approach and what we usually follow to write this algorithm codes into the controller and make it to function itself. That's the overall course flow, what we're going to have for today. That kind of gives you sort of an understanding on what we're going to discuss. Yeah. Starting out with the session here, it's very required to know how is the construction of a whole system itself as a part energy storage systems. So this is a very unique, just a general approach of how people put across the systems in place. We have a cell, then we have a module, and then we have a pack. This is typical approach. Most of the OEMs will be following it up because it becomes more modular in nature. It becomes more possible to scale it up. It becomes more possible to enhance certain performance requirements if needed. And also on the side, it becomes very easy to manufacture. It's easy to maintain the systems. It's easy to become testing of the systems and things like that. So that's why we usually have an approach like cell, module, and a pack. Not all the OEMs will follow this. It depends upon the pack size. If you have smaller packs, it's not really required to have like sort of a lot of modules. But if you talk about applications such as four-wheelers, I think definitely it is required from my perspective of design and development. So we will start from the cell, right? So that would be the first of the component. And so they are available in certain formats, like, you have cylindrical, you have pouch and prismatic cells. And then we bring them together and to form sort of a module. So how do we structure a module? How do we design a module? How do we set certain voltages for the module? What kind of current requirements should be set for the module? So those things are actually the part of the battery design course. We'll not talk much about here and those things. And then we put them into a pack itself. So when we bring out all these systems into place, this is a way actually all the OEs or startups will be following. Currently, would be definitely following the similar fashions in the future. So we would not talk much about other systems. So at the first part of the session, we'll talk about more on the cell side. And then on the next side, we'll not talk about the module in a pack, but we'll talk about how actually we ensure the safety for the module in the pack by using the battery management systems, right? So that's our focus for today's session. So next slide is about cell construction. And this is the most fundamental required slide. If you're not able to follow this slide, so it would be very difficult to understand anything further on the whole course itself, onto the understanding of a cell or a modeling of the cell, any of those things. So we'll start with the cylindrical cell, the image which we have on the cylindrical cell. So if you take a cylindrical cell, so it is way it is manufactured. So we have cathode and we have anode. So then we have what you say, a separator, which is visible here on the white patchy sort of a thing, right? So then we have an electrolyte, which is sort of filled between all these components into a place. So if you see here, cathode, where we have aluminum as a current collector. So on top of it, we would have composition of lithium. So you could call it as maybe it's a NMC, LFP, anything on LMO, all these chemistries, like that part of the cell which we define there, which typically sits on the side of a cathode. So how do we bind it? I'll just take you through here. We take a foil of aluminum, and then a specific sort of a paste of these compositions are made. And then they're put in a very systematic fashion, maybe using CVD, chemical vapor deposition, or PVD, and things like that. So a very uniform layer. So a material which is an active material, which we call as in electrochemistry, so will be binded with certain chemicals. So adhesives, you can call it as, and they're mostly rubber-based systems, rubber-based adhesives. So they will bind the active material to the aluminum current collectors. Okay, so that's the way the whole of if you take NMC, so nickel, cobalt, manganese, with lithium would be put over on that surface by binding them in the right fashion. So then we talk about anode. So we majorly use graphite on the anode. Apart from anode, so apart from using graphite, so we also use something like silicon, and we also use something based on lithium titanium, based materials. And then apart from it, we also been exploring few other materials for the anode chemistry itself. That's the same way they put those materials on top of the copper. So copper will be the current collectors, and the on the other side of the cathode, the aluminum will be the current collector. Then there's a separator in between, which sort of ensures that there is a specific cohesion between the systems into a place. And then there is this separator, which separates the anode and cathode, which ensures that there is no electrical short circuit between the systems. And then there's electrolyte, which helps us in ensuring that there is a a good ionic path flow, which is happening between anode and cathode, right? So that's the whole system put into place. I believe you kind of just got through it. We see some more details into a place here. So which is anode itself for the construction. I've put some images. We have done a cut section of the cell a few days back in our office. So if you see the anode side, so you have copper, and on top of copper, you have active materials put into your place. That would be, on this side would be a graphite. And cathode itself is visible here. It's sort of enhanced images from of the continuation of the past screens. So this is a construction which is visible on this side here. So it's very important. I know it's very fundamental, but I'll touch base on the advanced things, but it is fundamental to understand. So let's talk about the next slide, and here where we can begin really in the modeling side of it. Yeah. So now we know what a cell is, right? So when we have a cell in the whole structure, so we would subject the cell into various load conditions. If you could see here, what exactly this load is basically, when you're driving a vehicle, right? So if you accelerate a vehicle, then you require more torque from the motor. If the motor has to produce more torque, then somebody has to supply that current, right? So that would be the battery. So we have drawn a few specific characteristics here. There are different drive cycles. Let's say there's something called WLTP, FTP75, then MNADC, NADC drive cycle. There are various different types of drive cycles which we use for automotive applications for the testing of the powertrains. Or I would say the sizing of powertrains itself. Somebody who's in the racing application, you would develop your own race, drive cycles with respect to specific tracks and things like that, right? So when we talk about this, what we're trying to see is what is the current drawn from the battery pack. This is actually the model of Aether. We have done the simulation for Aether, and we got some values here on the screen here. So you could see that how actually the battery is trying to discharge with respect to the various drive conditions. So this is what the observation you could make from this. So the cell is subjected to various load conditions. It means like the current drawn from the cell is not constant. The current is varying continuously with respect to time. Because if you imagine when you're driving a bike, you're not driving with a constant speed, right? There would be acceleration, deceleration, braking. There is a humps on the road. There is a gradability on the road. There is extra person sitting in the bike. There's a load on the vehicle. So a lot of these conditions would put into a place. If you draw a certain sort of a current drawn from the battery pack, the whole thing looks something like this. So now we need to understand that there's a varying load. I would say as a rate of discharge on the cell. This is what subjecting the cell into. So the load is not constant, but the load is continuously varying. And then we'll go to the next one. So at the cell and a pack is subjected to. So when you're trying to draw a current, obviously there are a lot of reactions which is happening inside a cell, right? So when the reaction is happening, obviously they're exothermic. It means there is a heat being generated at the cell itself. So inside the cell, the cell, there's a heat generation within the cell itself. And the second thing is there is a heat also from the atmosphere. So if you take, in different cities, so that the temperature at different cities are different. So if it is a hotter temperature, so obviously that will impact the whole battery pack to be at a higher temperatures when it is operating. When it is a colder city, so where the temperature of the cell, because obviously the pack is in the vehicle, so the temperature comes down. So it means like you're operating a cell at various current points. The second thing is you're also operating a cell at various temperature points. So these are the two important things which derive the whole cell to operate in its own different regions. So now these are the two important parameters to understand anything about the cell fundamentally, then the way it behaves. So when you talk about temperature, the chemical reactions which is happening inside the cell definitely will vary because of the temperature. If you have a temperature which is very cold, the cell reactions will be very slow. then if you're trying to charge the vehicle at that time, then you would do some harm to a cell. So we'll discuss that, what kind of harm you could do. Then if you talk about if it is temperature is very high, there are certain materials in the cell. Then also there is a reaction that is happening in the cell, which is not supportive. The higher temperatures are not supportive. The reaction can happen faster. There are materials like SEI, the SEI start to break down. And then there is a lot of things which is happening inside a cell. So this is how cell behaves with respect to various different conditions. Like, you're subjecting the cell to various discharge conditions. That means you're abusing the cell continuously in a varying current loads. Second thing is they're also abusing the cell with respect to various temperatures. So when we have this going on, we need to understand how actually the cell will behave with these inputs, right? So when the cell behaves with these inputs, it is quite tough to know, how cell will be performing in a few days later, or a few weeks later, or a few months later. So when you buy a bike, electric bike, so what happens is, imagine you're going to drive it on the first day, it's all fantastic. Maybe the temperatures on the days, a month is very, very high. The battery pack would behave differently over those periods with the temperatures higher. Then after the next month, because you have put the cell into higher temperatures loads, then the way that the cell is going to behave in the next month itself will be completely different. It means like the cell is highly subjected to non-linear conditions. So objective of an engineer, I would say like us, who's a simulation engineer, is to study the cell and trying to predict how the cell is going to behave on X day or X number of cycle, depending upon its usage, depending upon the way we have subjected the cell to various different conditions. So that's why we perform simulation. And I'll run you through a few more slides to give you an idea how actually we perform, why do we perform simulations. So when we subject a cell with respect to varying discharging conditions, varying temperature conditions, there are a lot of reactions which is happening inside a cell, right? So there is something called lithiation of the cell and delithiation of the cell. So all the lithium will be sitting on the cathode side when we manufacture a cell, right? So when we first charge a cell, so there's a formation that's what we call as a formation of the cell. So a lithium which is on the cathode side would get when you charge a cell, so it transfers to a anode side, and then that's the process of charging. So when we are forming this process of charging, and then we are forming the process of discharging, the lithium ions from anode would transfer back to a cathode. So this is a process which is happening between the anode and the cathode. So this is what we call as a lithiation. So you lithiate cathode. It means you lithiate graphite. When we are charging a cell, when you're discharging a cell, you delithiate graphite, and you lithiate on the other side on the cathode. So this is a process which is happening when the discharging is happening continuously. So now when we form a cell, what is the meaning of forming a cell? It's the first time ever of its life after the manufacturing. The cell is charged for the first time, right? So when a cell is charged for the very first time, it forms something called SEI layer. Okay, it's called solid electrolyte interface, which could written it here, and also which is sort of visible on the screen also here. Okay, this SEI layer forms at the anode. Typically, there are a few theories also that it forms at a cathode too, but not really much into it. But this layer forms here. Why I'm talking about all these things? If you want, we need to understand why do we have to perform a cell simulation. An objective of performing a cell simulation is to actually predict how the cell is going to behave after n number of cycles. If you want to do that, we have to know actually what really happens inside a cell. Only when you know what really happens inside a cell, that's the only possibility you could predict a cell, how the cell is going to behave. And the whole discussion we're trying to do right now to get a solid foundation to understand how actually the cell is going to behave and what really happens inside the cell, right? So this is a very fundamental thing because the SEI is something depending upon its formation and deformation, the cell is going to build up certain resistance, and that really limits what we call as the power fading in the cell. And there are a few other reasons also, but this is a major reason. And the second thing is when depending upon the SCI layer formation, we also lose some amount of lithium. We'll explain that in further slides. So when we lose lithium, that's basically the active material. We're going to lose the capacity of the battery, right? So two different terms we're trying to start from here. That is on capacity of the battery and the power of the battery. What we call as capacity fading and what we also call as a power fading of the cell, right? So two important things. And whole of the life of a simulation engineer is actually to understand the whole process, why actually the power fading happens, why actually the capacity fading happens. If we can figure out this whole thing, then that's what we call as modeling the cell itself. And there are thousands of patents, that there are thousands of lakhs of research papers has been published recently on actually how we can understand this process of a power fading and a capacity fading. We'll get a little deeper in the further slides in knowing it. That's why it's very important to understand this one part that is basically SCI layer formation. Okay, SCI would be solid electrolyte interface, right? So solid electrolyte interface is formed when we actually make the cell, we form the cell for the very first time. And now this is good for the cell and it is required for the cell because if you see here, there is a separator and there is electrolyte which is there in between. So then there's a graphite on the one side, then there's depending upon the different chemistries, we have active materials on the positive side. So SCI forms, it's sort of a materialistic layer which is visible here, right? As you can see here, solid electrolyte interface. This layer forms. There are a lot of what we say chemical compositions of that SCI layer, but we'll not talk much about it. So what is happening? There's a graphite sitting here, right, on the anode side, and then there is a formation of SCI. That's a layer which is forming between the electrolyte and anode material, and then we have electrolyte and then you have a separator next to it, right? So I believe this is very well understood to all of you on understanding the formation of SCI layer. So why does it form? It's an electrolyte turns into certain form, and electrolyte certain amount of graphite which is on the anode, and then also some amount of lithium. So that they all combine together and they will form a layer on top of the materials, which is graphite sitting on the anode side, right? So if you imagine on this visualization here, I know this is all visualization because this is on like a microscopic level. So we definitely have to visualize all these things. So imagine this is like when the cell is newly formed, it's perfectly on the right side. Okay, there's a copper on top of copper. We have graphite being pasted with certain adhesives into your place, right? And now imagine when the cell is formed, you're gonna construct some sort of a material on top of it, right? So that is sort of I would say some sort of layer which get formed in here. This is a very, very important thing to get through it. So I believe you're able to visualize what we're trying to see here. This is a very schematic representation, and this is basically about sort of a very macroscopic visualization of that. Yeah. So this is what is forming, and now let's understand what further happens into our place. So let's talk about at anode side. So when we talk about at an anode side, so when we're charging a cell, when we're discharging a cell, so that is a very fundamental functionality of a cell, right? So we charge a cell, so we discharge a cell. So the foremost thing, it would lead to formation of SCI. Okay, so SCI is that solid electrolyte interface. That's what getting formed, and that builds up there. Actually, if you talk about SCI, then SCI is actually good for the cell in many different ways, but it has to be at a very specific limit. If you cross that SCI limit, I mean, the thickness of that SCI layer becomes bigger, it will be a problem. But actually, SCI layer is actually good for the cell, right? So then when we form an SCI layer, there are a few things which is also happening, that we're consuming lithium, we're going to build up resistance, and also we will talk about high temperature effect on the SCI layer, right? So let's start ahead with the SCI layer itself. So as we're discussing, this is a layer which forms on top of the graphite side. And when it is formed, during the formation, it has consumed some amount of graphite, and it has consumed some amount of electrolyte. It has consumed some amount of lithium, because lithium ions also, right? So it's a combination of these three things which forms the SEI layer itself. Now, if you kind of visualize, lithium ions are the one which ensures the capacity of the battery. It means the amount of energy you can store inside the cell is always depends upon the amount of lithium which is available for you, which is an active material, right? So when the SEI layer is formed, you consumed some amount of lithium to form the SEI layer, right? It is mandatory. There is no way you could just skip around it. There is a layer which is going to form, right? So you consume some amount of lithium ions. It means that the cell has lost some amount of capacity when the first charging is done. And then when you keep on charging and discharging cell, charging and discharging the cell, depending upon certain situations, the SEI layer forms and deforms. It means the SEI layer is formed because of certain conditions. I'll talk about it in the next slides. It gets deformed. Again, the SEI layer is going to be formed. When the SEI layer is going to be formed, then some more amount of lithium is consumed. So when this processes keep on happening, what happens actually, we lose lithium. When we lose lithium, we're going to lose some amount of capacity in the battery pack. So it means when you brought the cell for the very first time, it is, let's say we have 100% capacity. It means like we have all the lithium. Then obviously when you form the first charging cycle, we will lose some amount of lithium. So then a small amount of capacity is fitted. The same way, this things keeps on progressing, right? So when this things keeps on progressing, the SEI layer possibly start to become a little bigger and bigger and bigger in size. So what would be the size of SEI layer? It would be in specifically on nanos. So that's what is the size of it, and it start to build up. And then what happens is you're going to consume some amount of lithium. And if you understand this progressive way, more number of cycles you're trying to operate under, it means like a more lithium is consumed. The more lithium is consumed, the capacity of the cells start to come down. Okay. And now let's understand a little bit about this itself. So the formation of SEI layer, right? The formation of SEI layer is subjected to amount of temperature the cell is subjected to. Why it is subjected to the temperature? Because the SEI layer is formed. If the cell is subjected to a higher temperature, the SEI layers start to break down. The moment the SEI layers start to break down, then the SEI again gets formed, right? Because there is a reaction of electrolyte with the graphite. Then the SEI is going to be formed. The moment the SEI is going to be formed, again you're consuming some more amount of lithium. Then there is a capacity loss in the cell. So now this processes keep on happening, right? If that's why it's very important why we talk that do not let the battery to go above certain temperature. When you go it above certain temperature, there is certain reactions which are happening. Those reactions are leading to loss of certain SEI layer. I mean, this is one of the parameter, by the way, not everything about temperature. So then it just kills out certain SEI, and then SEI again forms, then it consumes the lithium into a place. And by this way, you are actually consuming lithium and the capacity is getting degraded. Then the second thing, when we're trying to draw too much of current out of the battery, like what we say higher discharges in the cell. So again, there is some reactions which is leading to a higher temperature. When you draw a higher current, right, there is more reactions happening. The more reactions means more temperature. This is also again decomposing SEI, then again forming the SEI. So this is a process through which the SEI is getting affected at a one point of it, right? So now, if you understand this perspective, the SEI is a very, very fundamental step through which we are trying to get through the way how the cell is trying to build up its resistance and build up loss of capacity. So the moment and the SEI layer forms, right? There's SEI layer going to be formed, and the SEI layer is being formed. What happens? You're going to lose. The cell is going to build up some resistance. Why the resistance is happening? Because when you want to understand the cell level reaction, so the lithium has to get intercalated between the graphite when the charging process is happening. Now, when it is discharging, it has to go out of the graphite structure and it has to go to the anode side. So there is a continuous process of exchange of this. This is happening, right? The lithium ion is happening. Now, when there's a layer being formed, it builds up a resistance, right? It means it is a little tough for the lithium ions to go through and then get through into a phase of a graphite. And so this process is building a resistance, right? So then if we understand this one, so the resistance being built, this resistance will let not the more power to be discharged from the cell, right? So we could very barely understand how we're losing the capacity and how we're losing the power from the cell over the span of time. And the very, very challenging thing is because this SCI is highly complex in nature, the way it forms. The whole idea at electrochemistry level is actually to perform certain studies, then predict how SCI is going to be formed. The way you accurately predict the formation of SCI, you're going to predict how the cell is going to behave and how the number of cycles are going to be there for the cell, how the health of the cell and all these things. This is what happens at the SCI itself. So we discussed about a few points here in the SCI. So there's a lithium being consumed at the SCI. So then the resistance buildup also, which has happened because of the SCI layer, right? So then because of the temperatures, of higher temperatures, you have increased the decomposition of the SCI, then the reformation of the SCI, then consumed some more lithium, built up some resistance into the cell. So again, that's how actually the higher temperatures affect the ACI, and then higher temperature will form bad into the cell, right? That's why we always tell, let the cell to be always optimally operated within the certain temperatures. So if you go and operate the cell above its specified temperature, a lot of bad things will happen. And those are the few bad things which we're trying to talk here about it. So now I talked about the first point, right? Then on the higher temperature side, there is one more thing on the lower temperature side. So I would like to know if anybody can just bring up your answers into this, kind of discussion. What really can happen at a lower temperatures, right? Now, anybody can just drop your answers over there and let us know, what really happens at a lower temperatures, right? I'm here to get some answers from your side. Just put your perspectives. Nobody is right always. Just put your perspectives. According to you, what can really happen at lower temperatures, right? Because when you buy a cell, it is very specifically defined in the cell data sheet. Do not subject a cell above and below certain temperature values, or operate a cell above or below certain temperature values. Now we talked about our higher temperatures and few of the perspectives of higher temperature. What do you think on the lower temperature things can happen? So low flow of current, formation of SCA layers inhibited, effect of building lithium ions, less resistance, right? So great, thanks for dropping few answers here. So let's talk about a lower temperature. What really happens? At lower temperatures, what really happens is, the reaction rates are very, very slow, right? So if the reaction rates are very slow, you should not actually charge or trying to discharge a cell. So you should not basically do much of the activities at that point. You should basically try to heat up the cell to a very specific temperature and then let the cell to be used. But let's say we can't tell all this into a customer, right? Like customer, boss, like don't tell me all these things that when I should use my bike or when I should use my car, because if the temperature is low, do you think you should say me that I should heat the battery and wait until it all becomes all good and then I can use a battery vehicle? That's no way customer is going to listen to us. And let's say customers park this car over the night, and that day night the temperature has dropped really, really low, and he kept the vehicle for charging. Then at that time, we can't even control, right? Basically, so there is no way you can just control the temperature and atmospheric temperature and tell, okay, this is the way it should behave. So what really happens at that point is, when the temperature is lower, the cell reactions are very less. When we try to charge the cells, so a lot of lithium will come and start to plate over the surface on parts of the SCI. And then we could call that the process is called lithium plating. Okay, that's what possibly would happen at most of the times. It means you're trying to push out the lithium from the cathode side. So it start to come out and try to get, just because there is a lower cell reactions, it start to form. And that is what we call as lithium plating in further cases. So in such lower temperatures, the things will happen of that sort. Not really, I would say it gets thicker. We could discuss the QA sessions. It's good to know, on the discussions. So QA, I'll come up with a QA session. We'll take these questions right there because it will kill the flow of the whole discussion, the presentation as a part of it. So like in this, say, there are many things which happen to the cell. So, maybe another example, if I can give you, is when we keep on using a cell, as I was discussing in the very first picturized representation of how cathode is formed. On the copper side, you put graphite. So it's a binding of certain materials like adhesives. When you keep on using a cell, the binding material will lose its capability. And sometimes even the copper get exposed and the copper get corroded, and parts of copper will come into the electrolyte layer, and they again enhance that possibility of forming an SEI. Then we call it copper corrosion in few cases. And in some cases, there will be a small amount of water which will be left inside the cell. We do not want the water to be there, but you cannot just take out all the the molecules of water or vapor-sized particles in there. So then what happens over there is when the water is left inside the cell, I mean, I would not say like droplets of water, a very, very less amount, even very, very small size of water. When it is over there, it forms certain types of fluoric acid because electrolyte has certain chemistry. It forms a fluoric acid, and that fluoric acid is again bad. It forms really inside the cell, okay, during the reactions, okay. So then the cell it eats up some amount of SEI layer because it's a fluoric acid, right? Again, definitely fluoric acid is dangerous, but inside the cell is already dangerous. Like this, so many things are happening, inside the cell itself. So these things actually are the stuff which is on the anode side. Okay. So now, if you want to be an engineer on the simulation side, right, and you have to be understanding about various of these parameters. Maybe if you take each of these parameters, that itself will be a discussion for like 2-3 hours in doing some calculations, in writing an equations, in knowing what really forms in SEI layer, how fluoric acid is formed, how the copper is dissolved, and what really happens. So like it's a very deeper discussion in terms of what we can have. But I'm just, because it's a very small session, I'm trying to limit myself. If you're interested, we do have advanced courses, you can look forward for that. But I believe you kind of understood what is really happening on the very basic overview, what is really happening on the anode side. The same way, at the cathode also, there are certain things happening. Okay, those things would be resolution of active materials. I'll not go much deeper because I believe we kind of got an over on what happens on the anode side. It's pretty much similar on the side here. So active materials means we have, if it's cells, nickel, manganese, cobalt. That manganese is kind of very small. It tends to drop down into electrolyte. That is what we call as dissolution of active materials into the electrolytes. It also sometimes try to come through a separator because it's very small in size. We call as anode poisoning because the manganese can come out through that layer of separator and it get deposited over the areas of cathode. So a lot of things happens on the cathode side too to affect the cell to go bad over the time. You can very simplistically call it aging the cell, right? And there is something called structure collapse. So when there's a specific structure, right? So because lithium is there in between all these the components of active materials. So now when the lithium is taken out, when the charging process is happening, the lithium is taken out. When the lithium is taken out, obviously there's a very nano level gap, right? So when we take a lot of lithium out, then the structure itself collapses. We call this structural collapse of the structural collapse of the cathode. And then obviously the binder materials. The meaning of binder materials is we discussed about all these active materials are mixed with a binder. It's sort of an adhesive glue, which helps the active material to stick to the current collector. Over the span of time, that also becomes looser. It loses its adhesive capabilities. And obviously when it loses adhesive capabilities, there is no proper contact between the current collector and the active material. So there is no right amount of transfer of the electrons and things like that. So current collector corrosion, as you said, on the anode side, how graphite is tend to form, corroded, and the same way on the cathode side too, the aluminum start to, kind of form certain corrosions and stuff like that. So a few things also happens on the cathode side, a few things happens on the anode side. So if we understand all these things, and that's actually the way you could get deeper in knowing why the cell really failed, how the cell really, tend to lose its capability over the span of time. I believe my discussion over the last 30 minutes, 35 minutes, kind of brought you an idea about how actually cell loses its capacity, and also it loses its power, right? So two very, very important things in terms of capacity fading and power fading into the place. So when we understood all these things, so now if we want to kind of simplify all these things, this is sort of electrochemistry side, right? This is more discussed from the electrochemistry point of it until now. But as an engineer, as an application engineer, where people work on the sides of application engineering, they would not actually go to the very chemistry level, right? So because that's a very different way into a place. There are companies like Samsung, LG, Panasonic, ASCE, Cal, many companies, they're working in chemistry side. I think they would have more engineers working more on that. But actually there are, because we interact with a lot of companies in Bangalore too, every company, like, if you take Bosch or suppliers like Exicom, Ion Energy, when they buy a cell, they just can't trust the suppliers. And they also have engineers at a chemistry level to identify the cell level reactions and what really happening to the cell over the time of it. You can test a cell, see how things are bad happening inside a cell by cutting the cell, taking the microscopic views of the cell and things like that. There are a lot of opportunities over there too as an application point of it, but at electrochemistry point of it, there's a lot of understanding for physicists and chemists, electrochemists into a place. So now, because of all these things, something is happening in the cell to lose its capacity and to lose its power. So if you come back here on the screen, what we're trying to see here is an application point of it. Okay. Now I have a cell, I purchase a cell. So before purchasing a cell, all these things done at the chemistry lab. Now I purchase a cell. So as an application engineer, what I understand is these graphs. Okay. This is the we get when we actually test a cell. So all these things are happening inside a cell. Now what I do, I buy the cell, I test that cell by using a test equipment or putting the cell into real-time conditions and stuff like that. So we understand the functionality of a cell from this perspective, which is visible on the screen here. There are a couple of graphs. What we're trying to see here, we're trying to discharge a cell. It means like discharge is the process where you draw out a current from the cell, right? So we're trying to discharge a cell at various different levels, okay, various different currents. So sometimes I'm just trying to draw 1C out of the cell. 1C is like equivalent to nominal capacity of the cell. So I'm trying to draw 5 amps, then I'm trying to draw 10 amps, I'm trying to draw 15 amps, 20 amps, 25 amps. When I'm trying to do that, we can observe a behavior of the cell that the cell is actually trying to follow different paths. It means that the cell voltage, right? So if you draw a cell at 1C, it exhibits a characteristic which is in the red color, okay? So which is a graph which is represented in the red color. Then if you're trying to draw, I'll just try to take another color of a pen. So if you're trying to draw the 5 amps, okay, maybe depending upon the nominal capacity, let's say 18650 25R 2500 mAh, it means 1C is 2.5 amps, okay? And then if I'm trying to draw 5 amps, that is basically 2C, right? So the cell behaves at different characteristics. It will follow this pinkish line. So it means like when the cell, you draw more current, the cell is going to behave in a different way. And then at a 10 amps, it is operating a little different way. And you can see here that somewhere 2.5 amps is a fully charged cell, right? If you take like a 1.25, that would be the 50% SOC which you define in this region, right? So if you want to know at 50% SOC, the cell is at various different voltages with respect to operating. If you discharge a cell in specific manner, it exhibits a very specific behavior, okay? And area under this curve will always give us the energy you can utilize, right? So if you understand, when I'm trying to discharge a cell too much, it means like a too deep, you tend to get only a specific amount of energy. And when you're trying to draw a cell at a very specific way in terms of, let's say, 1C, that's nominal capacity cell, so you'll get possibly the more amount of energy, right? So it means that, imagine when you're driving a bike, right? When you're driving a bike, you're not constantly drawing a current. If if you remember the first few slides, we're driving a vehicle, it's undergoing a acceleration, deceleration, gradability, a traffic signal, so many like a lot of things, right? Humps and bumps. Imagine the way you drive a vehicle, exactly the same way the current is also going to be drawn from the cell. Okay, I'm just giving a relative example. You accelerate, just correlate that way. I know it's not 100% right, but just correlate that way. You keep accelerating, it means like you're trying to draw like just ups and downs of current, right? So when you're trying to draw that, it means that the cell is continuously behaved at various of these points, right? It means it's not just constantly drawn like this. It means sometimes you're drawing 0.5C, sometimes you're drawing 2C, 3C, 4C, sometimes you're coming back directly to 1C. Then sometimes when you do a regenerative energy, you're charging the cell back, right? It's such a non-linearity of the system. So straight, and this is actually a lab case test condition that you're just trying to test a cell by drawing a specific amount of current. But when you do a real-time testing, on the vehicle, the cell is drawn like crazy all over the graph, right? Ups and downs. Now we'll come to that, why I'm trying to stress all these points and all these points into a place. Now as a simulation engineer, you got to visualize, goddamn, how I can put all these systems into a place and predict the cell life and predict the cell's behavior over X span of time, right? Then the other graphs, which is in the other side here, I'll just run back my slide and clean it up. If you see here, this is the temperature graphs on the other side, okay? When you're trying to draw a X amount of specific currents, the cell is trying to exhibit specific temperature outputs. So it means like when you're trying to draw an X varying amount of current, that the cell is trying to produce varying amount of heat, okay? So it means like it is totally unpredictable that what amount of heat is being generated, right? It's such a complex system into a place. And then now if you understand this characteristics, and this characteristics is only for this specific cell. And if you take another cell, like which is mentioned here, right? This is a Samsung cell. I can share you where I got these graphs. It is Samsung INR 186025R, a specific chemistry of a cell. These graphs are, specifically to this specific cell. Now, when you take another cell, that cell behaves totally different. And you cannot just compare this cell data to another cell data, right? So it means, imagine the complexities are growing one by one. Now, as a simulation engineer, we're trying to come across to visualize how you can put all these goddamn things and trying to predict what is the cell behavior, right? I'll run through a few more slides here, which kind of gives you a more complex view of a cell modeling requirements, right? So if you see here, temperature dependence of discharge curves, what it means is, depending upon a specific temperature, the amount of discharge currents you can draw from the cell is also going to be varied, okay? So it's again a complex approach, right? So because imagine that data temperature very high, we don't have a thermal management system in the battery pack. It means like there is no systems. Then because of the ambient temperature, so the cell is increase its temperature because ambient temperature is also higher. That day when you drive a bike, the way amount of distance you can travel will be different. Like imagine that day temperature is 40 degrees Celsius. Maybe you just get only like custom companies from just 60, possibly that day you're getting only 55 or 57 kilometers if you do not have, let's say, thermal management system. And these temperatures at that time, they are also affecting the life of the cell. Maybe the way the cell behaves after a few cycles will be different depending upon the temperature we have subject the cell into, right? So this is a way how temperature will affect the cell. So it will affect the cell at that point, and it will limit the amount of current you can draw from the cell. Because if at a higher temperature, you're trying to draw more from the cell, you're going to increase the temperature of the cell, then you're going to make more bad into the cell, right? So again, this is a functionality of a BMS. BMS knows what temperature is right now in the battery pack. It limits the amount of current which can go to the battery pack. We'll discuss that in the BMS section, right? So when you come to here on the point of it, that the temperature is very, very critical, which affects the cell's performance and cell's life also. Then there's one more amazing thing that would be, we call it as resistance of the cell. Okay, so you call it the internal resistance of the cell. We have very barely understood, because of the SCI layer, resistance is getting built up, correct? So this resistance getting built up within the cell is not only because of SCI, there are a few other parameters also which affects the resistance of the cell, right? So you could see here that a very clear definition in terms of how actually the internal resistance varies depending upon amount of current you're trying to draw from the cell, right? So if you could see here, there's specific numbers if you're trying to draw a current, and there are very specific set of graphs there which represents the the internal resistance of the cell. Okay, so why I'm stressing on all these things, because without understanding any of these things, people teach simulation, using a MATLAB. Okay, put some X block, Y block, Z block. There's just no point just learning something tool-based learning, right? You're respected only when you know why we are trying to do that. Okay, that this course is actually to set your fundamentals very deep into the roots, to know why we're trying to perform a simulation, and actually motivate the performance, gain a very, very deeper insights, and then something is happening. Okay, this is good for the cell, this is bad for the cell also, right? So then on the other side of the images, which is here, the internal resistance of the cell also varies with respect to temperature. And see, internal resistance of the cell varies with respect to number of cycles. Okay, so now imagine a differential equation. Your differential equation becoming complex and complex and complex just over the spans of moments here, because resistance is varying with respect to amount of current you're drawing, x, d of x. Then there's one more parameter. The resistance is varying with respect to amount of temperature of the cell. Then another parameter. Then we give another parameter, which is like a cell cycles. Like depending upon number of cycles, the resistance is varying. Then in the previous graphs, depending upon the cell subjects a specific behavior of the voltage. And amount of current you draw, the cell increases its temperature. Goddamn, if you keep on building all these things, your order keeps on increasing. It means the more number of parameters, the more complex the system is to solve to get the answers, right? So this is one part of the cell, and then there is some more things about how the cell life will get affected. Okay, how the cell life will get affected depending on the amount of current you're trying to draw. If you draw a lot of currents, like somebody was asking, how actually the cells higher discharge currents. Like if you always try to operate a cell at higher discharges, the life of the cell drops down specifically the way you drive. So very realistic example, if I can give you, the cell, I would say the life of your vehicle, if you bought an electric vehicle, if you do it very peppy, if you drive it very peppy, it means like you keep accelerating like good things are, so then definitely you're drawing a lot of transit currents out of the cell. It means you're trying to operate at higher Cs. Then obviously I promise you that your vehicle will definitely, your battery pack will definitely get affected for that. So it means like now the range, I would say the capacity of the battery pack over a span of time depends upon the way you drive the vehicle, right? So like all these things, put them into together. So I come to the slide, which is here. Hola. So lithium ion, how can we understand you, right? So it's a goddamn complexity, which is totally unpredictable into nature, but we are the engineers, sort of physics and sort of mathematics into a place to put into a structure where we can actually understand and predict how the cell is going to behave within its utilizable cell life. Okay, so that's the point of it. Now, if I can that how actually we can perform and how we can understand a lithium ion cell is in two different ways. You can test a lithium ion cell. So when you mean the testing, I'll show you some of the images in the next upcoming slides. See, if you're using a cell, if you take a bike or a car, how many years are we going to use a bike, right? Like, let's say for a very good reason, very healthy reason that I'm going to use a bike for 10 years. And then I'll forget 10 years, like it's very hard to predict what happens for 10 years. Let's take what happens today. And I want to know after 1 year, how much range I can get. After second year, how much I can get. Third year, how much I can get. Fourth year, how much I can get. By end of fifth year, I want to know how much I can get a range, right? If you want to do that, then actually we have to subject the cell to this testing conditions in real time. You buy 1,000 cells, put them in various different testing conditions, different temperatures, different discharge conditions, different I would say, environmental exposures and things like that. Study a cell for 5 years. Really, we think that we can study a cell for 5 years and then we can use those cells in the vehicle applications. By the time we study the cells for 5 years, the new cells would have been coming to the market. By the time the cell would have been already obsolete, right? It's not something that we can actually do fully to actually release a vehicle, right? Because how many years I can wait to release the vehicle? Today we are talking about 3 years at max, like 3.5 years, 2.5 years, 3 years, 3.5. Is a pipeline into the market, right? So if you want to know actually how long you want to check the cell behavior, it is no way possible to do a real-time test. But we do perform real-time tests because we want to know how really it performs, because we can't really believe on all the simulations every time. So we have other side on the performance, right? The perform simulations. That's the best way. You can always perform simulations and you'll be able to actually predict the behavior. So I believe that's how you got why we are trying to come to this point and understand why we perform simulations itself. Okay, so I will go here and show you a few images, and then by end of the slides on the cell, we'll take a small break. So this is actually the cell testing facility. I would say the cell aging facility, which is there at Aether. I didn't visit the facility, by the way, but this is published in the Aether's blog, which is link is given in the about top there. So which tells you that how Aether is trying to conduct aging of the cell and trying to predict the cell behavior, right? So it means that they're trying to know how the cell can behave over a span of time by really testing them. Okay, there are test equipments. We call them as cell cyclic testers. They're valuable, goddamn expensive in a few cases. So we use these cell cyclic testers. It means this is a practical way of understanding how really cell behaves. Okay, as I told you, like if you want to release a vehicle and you want to promise a vehicle is going to give this much of proper range and with respect to this battery pack, you would have to perform this kind of a test too, right? And this is one of the way, and it means like why all these things will come at the last, why we have to do so much of complex ways in understanding. But for sure, we can't actually perform so many tests just on this test benches. Okay, so we have to perform simulations because there are 1,000 different ways how cell can behave. Okay, 1,000 different ways customer users said, 1,000 different ways how it has been abused into a case. So we can't perform all this like real-time tests in all the cases. So we have to perform simulation. That's where the simulation engineering is very necessary for all our engineers out there and looking forward to get into the area. So what type of simulations which we perform? There are different approaches to perform a simulation. Okay, so there are methods like electrochemical method, and that's where we talk about more on electrochemistry based approaches, because as I said, there's so much happening inside a cell. It becomes very complex to these models and perform all the studies to know how we can actually put things into a place to model the electrochemical method. But there are software tools available. There are like things people are working on. It's necessary, but the people are working on them too. The other side, we have an electrical methods we call equivalent circuit methods. Okay, which you could see here. There's something called a Thevenin model, RINT model, runtime based, impedance based, Shepherd models, and things like that. So those are methodologies, I would say, and approaches through which we can actually model the cell. Okay, so what is just basic funda about it is like imagine you could represent, like if you're from a mechanical background, let's say, take this example. We have done that UTM machine, right? So we take a round shaped test piece and we put that into the UTM machine. We apply a load, elongation. Then the material behaves in a very specific way. It stretches to elasticity, and then it breaks after the plastic deformations, and then the material breaks. Now imagine, can I actually create an electrical representation of this real-time system? Yes, I can do it with our impedance, resistance, based circuits, like the RC circuits, which you can call it in the simplicity. The same way, we can represent the complexities of all these behaviors within an RC circuit, and that's what is electrical modeling-based approaches are. And that's what the model approaches also we have built, and we have consulted a lot of customers. We also teach those model-based approaches in our advanced classes too. And how do we actually model them? Okay, and for the slide here, what we can get by performing cell simulations is something, right? Because we just say, okay, I'm going to perform simulations, but actually, why we try to perform simulation? There are a few reasons here why we perform simulation. We want to know how cell behaves over a number of cycles. Okay, that's very important thing, because I want to know after a Xth cycle, our nth cycle, how my cell is going to be there. And then we want to understand with respect to different temperature, how the cell is going to behave. We want to also understand, depending upon rate of discharge, how the cell is going to behave. Then how actually cell resistance is being increased over a span of time. We want what sort of degradation behavior is happening in the cell. I would relate that SOH and SO degradation is something quite relative. And I want to know SOC of the cell. So SOC is a very, very deeper term to understand, and it's not just straightforward, right? If you're now seeing that, if you want to know at what point what is the SOC, today when you predicted an SOC, but after 100 cycle, the SOC point will not be the same for that kind of specific discharges. So you need to have a very dynamic cell model to actually predict to the right SOC numbers. Okay, so here I'm just trying to kind of put across in a very simplistic manner that linear identification and nonlinear identification. It's very easy actually if it's a linear system. You know how it actually behaves, but it is a nonlinear system, which you could see here on the downside, and it's quite complex to predict that. If that nonlinearity is actually with various number of inputs and an enormous number of inputs, it becomes a highly complex system itself to predict and to know how we can actually tell a state of the system. Okay? So that's about the nonlinearity of the system. That's how the lithium-ion cells are, and there are so many various parameters which are affecting that nonlinearity. And now a job of a simulation engineer is to model it and trying to see and predict how I could just check it out and ensure my answers are always correct and then I predict the model. So putting a very solid foundation on understanding in terms of very fundamentals of cell chemistry, I would say approaches of why cell behaves as specific characteristics, and why cell undergoes capacity fading and power fading, and coming to the points about how actually certain parameters affects the cell life, how actually application engineer looks at the point by seeing the graphs about the cells, and then on the other side, actually how system is nonlinear and what actually we're trying to predict with respect to simulation risks, right? So we went through all of that, and here's the Q&A session. If you have any questions till now, you could just drop in the questions in the chat box. I know there are a lot of people participating, even on the Zoom here and also on the YouTube here. I'll try answering, or else we'll try to see through if you can actually put sort of an email based, or else we could put all this QA in our LMS website and then put the answers over there for you. Awesome. So I believe until now it gave you a very good fundamental understanding. So I believe so very happy for that. So let us know if there is any feedbacks that I went too fast. There are certain things which are not clear. So let's try to put them into the email and then try to see how we could just answer to you all. Okay, so if you have put the questions in the very top, just please copy them and paste them in below, so it becomes easier to. The possibilities of SCI poking the separator on short circuit. Rams, yeah, that's absolutely true. There are a lot of chances that this lithium plating, we call dendrites, they just become sharp and flaky, and they just puncture the separator. If the separator is punctured, like the rest is all about the bad things of circuits. Chances with plating like that. Is overcharge and deep discharging causes more SCI? Absolutely. If you know, the electrolyte is very stable. This is an answer for Samiran. So if you're trying to overcharge a cell, it means that you're trying to go above certain cell voltages, and the electrolyte is unstable at higher voltages and lower voltages. So if you kind of tend to do that, then definitely will affect the cell's life. It will for sure form different so okay, so just for few people want to take a small break. It's 6:39. We'll take a 10 minutes break. I think we'll not take 10 minutes. It will be too difficult to start the session. So we'll catch back at 6:45. So yeah. So until then, just take some fresh air and grab some cup of water or tea or something. So we'll catch back with a fresh mind to conceptualize more things. Yes, also, okay. So, lithium is the main focus factor. We know lithium as highly reactive material. Okay, is heating only heating, nothing explosion or okay. So lithium polymer explosion, YouTube. The battery with stones, it's just lead to damage the internal protection system and the catalyst contact. Polymer itself has different construction itself, but yeah, don't go if you want to really because become a YouTube vehicle because time that pass, and these regulations are not easy to pass if we just if you try to abuse. What could be the reasons of okay, so just for a second, I went offline and came back. I'm not sure you were able to hear me or not. I was trying to share a screen. I think all of a sudden things went bonkers. Cool, I think I'm back here. Maybe we could all get back in here. Okay, so okay. One more question is deep discharging. I answered that. Could you please explain the lithium plating? Okay, lithium states, at a lower temperatures, the less reactions are happening, right? So when you're trying to charge the cell at the time, or even sometime about like when you're trying to charge the cell, so you're trying to force the cell to make a reaction. You're trying to push out the lithium ion from cathode. When you're trying to push out the lithium ion from the cathode, this is happening on the anode side because of lower temperatures, and that just tend to form and sit the layer over layer over layer. And there are some formations of like lithium ions become metal. Putting across equations, I don't have them on the screen right here. There's a specific type of reaction which happens between the lithium ion and other graphite. So they tend to form a lithium metal. Lithium ion becomes lithium metal, and that's the way lithium plating is happening. Maybe I can put across this in detail. I can put across the equations also. Does the load affects linearity? So Ramya, yes, absolutely. The load will affect the non-linearity. There is no doubt on that. How we receive certificates upon payment? You will receive the certificates through email. I mean, all the certificates will be sent through emails. Yeah, so that's about it. It'll just be sent within like 2 days, once like 2.5 days possibly. Okay, just 1 minute to go for 6:45. Just give me 1 minute here. I'll just take some water and I'll just join back into the session. I'll just muting myself for 1 minute here, so kindly excuse me. Thanks for being back. Just trying to take some water. I've been speaking for close to 1 hour. So there are a lot of questions. Fantastic to see all the questions. I would be very happy to to answer all of them, but as a limitation of time. But I would definitely stay back after 7:30 for a while and try to put the answers to the screen. So kindly hold on for the people. So if not, we could have another few discussions through the offlines too. Yeah. So by ending the session on the side of cell, we could start the session on the BMS side. Okay? So understand the things on the BMS side. So why do we need a BMS, right? So people are very crazy, and people want to know why BMS, and a lot of people want to work on BMS. But it's very much essential actually to understand why we need BMS, and also in a way that how complex the BMS is, because which kind of brings you more in developing these better BMSs. In-house BMSs in India, we could make our country great. Yeah. So ensure the cell safety and a pack safety and a life of the cell. So two very, very important points. We want to ensure the safety for the cell, and that's the highly primary functionality. And then the second is the life of the cell. So the one is about safety and life, both related to a cost. Because imagine you're putting the battery pack onto the vehicle, you release 10,000 vehicles. By some mistake inside an algorithm, or some mistake inside battery design itself, pack design itself, if something goes wrong, imagine replacing cost of those 10,000 battery packs. That's a whole lot of money, right? Because the battery pack constitutes close around anywhere between 20 to 40% of the vehicle cost. That's a lot of money to put into a place. So that's one of the things. Second thing is, imagine if there's a certain safety failures, if the case that the pack catches a fire, the company would be sued, and the millions of dollars has to be paid to the customer to provide compensations, right? So, and also the life of the cell. So you promise to the customer that the vehicle is going to give you X range. I'll come to that. Ather is promising 3 years, and Tesla is promising like I think 8 years or X number of kilometers and things like that. when you promise to a customer that, okay, boss, you're purchasing the vehicle and for 3 years you drive it, 70% 70% of the range is going to be there after 3 years. At 3 years, third year end, it means like you're getting 100 kilometers today. It means after 3 years you get 70 kilometers possibly, right? If imagine the vehicle is going to only give 60, it could be because customers abused it. Maybe he's using in the hot temperatures. Maybe it has salt conditions. It has like customers put extra load on the vehicle. Maybe he was carrying the luggage on the vehicle always. Maybe the big basket brought it. They keep carrying the load on the vehicle. All these things, like you're subjecting the vehicle, and then again the cell deeper manner, and then things can go bad, and then you have to claim your warranty, right? Actually, you have to replace the battery pack for the no cost. So when you do that, it's a lot of cost. So it means like you need to predict the life and ensure that the life is always there, and at least the bare minimum. Everybody want to cover up their things, right? So till the warranty, you need to ensure that. So customers are also smart that they can take the things through any channel. So it need to ensure the safety of the cell. So on life of the cell. So when we want to do all these things, we need a BMS. That's a battery management system. So two important things. The one of the primary functionality would be cell safety. The secondary functionality would be the life of the cell. There are a lot of other things also. They're very important. They're very, very important. Maybe we could discuss if the time permits in here. So BMS does functionalities such as cell protection, okay, or a pack protection. So why we need to protect a cell? There is something called over voltage and under voltage. It means when you're charging a cell, so there is a limit for the charge and the discharge voltages. So every cell has a specific cutoff voltage. When you download a datasheet, I recommend you strongly download a datasheet. Some datasheet like ICR 18650-26F, Samsung. If you download the datasheet, you can see under voltage cutoff, over voltage cutoff. Over voltage will be like somewhere around 4.2, under voltage will be around 2.5. I'm telling you, this is not for all the cells. Each cells have different voltages. Okay? So how the voltage of the cell is defined? It's defined with respect to cell materials like on anode side and the cathode side. We call it most electronegative material, electropositive material. It depends upon the cell selection, the potential voltage. So why we can't go above 4.2? Because if you know from fundamentals of electrochemistry that's the maximum voltage difference in the electrochemical series that never you can ever get. Parameters in terms of the active materials you can put there on the cell itself. So coming back on the functionality of the BMS. So we ensure that cell is always protected between the over voltage and under voltage. It means like when you're charging a cell, you're charging a cell from, let's say, an X value, and the charge keep on going and the cell reaches a 4.2. So you need to cut off the charging. So imagine if the charger is faulty, if the BMS is faulty, it did not cut off the charger. What is the cut off in the charger? It means there will be a relay contactor in the very electrical terms of an EV. So it did not open up the contactor, and then you keep charging the cell, then it went above the specific voltage. When you go above 4.2, then things will start to happen bonkers. It means like there is a formation of gas, then that increases the pressure in the cell, that tend to venting. Then if the pressure increases still, the cell breaks down, and then the next thing what you hear is a fire. So this is how things will happen if you do not protect the cell over the voltages. Okay. So now, if you want to do that, then you need a BMS. It's basically an electronic circuitry which constantly measures the voltage of the cell, and then ensures that if it is hitting 4.2, cut off the charger, right? And then it is not the way actually you do it. There are a lot of algorithms through which we ensures the upper voltage cutoff. It's not like you wait until 4.2 and you cut off. There is certain things like which we discussed below in slides. I'll run you through the industry way of doing things. Then on the underside, what means like when the cell is discharging, so it goes voltages below voltages. If you remember the first ever image, like few images, I've showed a graph of discharge rate versus temperatures and things like that. The cell is behaving in a various different voltages, right? So when the discharge means when it reaches around certain lower cutoff, you need to cut off a cell. It means like cut off the discharge. Imagine you're driving a vehicle, and when your battery shows 0% SOC, or you're using your phone shows 0% charge. it means like phone will automatically shut down itself, right? It doesn't mean that the battery is completely gone dead. There would be a small possible charge still left, but it is not safer actually to go below that under voltage. If you go below under voltage, you could do a lot of bad things to the cell. Then there are electrolytes are unstable in that region. There are a lot of bad things happening in the chemistry side. So you could basically ruin the cell. Imagine you still do that, and then your cell life is going to be reduced in a very simplistic manner. So you need to protect the cell from over voltage and under voltage. If you want to do that, you need electronic circuitry. Cutoff means, okay, when you reach that voltage, open the circuit. It means don't let the system to further continue with the charging or discharging process. Overcurrent, when imagine you all know about short circuit, right? The same thing happens in the cell, or else like externally or internally. Internally is very difficult to do, predict, and then observe. Maybe you can observe with temperature as an output parameter for a measurement, but it's very difficult to predict an internal short circuit. With the external short circuit, if you're trying to draw a lot of current out of the battery, there's a sensor on the BMS, that's the current sensor, which measures, and the BMS internally knows what is that upper current limit value. Depending upon knowing that upper current limit value, the BMS will automatically restrict the amount of current the battery can draw. So like this, it does thermal protection. It means it doesn't let the battery to go above certain voltages, or it also doesn't let it to go below certain temperatures if it is having thermal systems like heating and cooling systems. So pre-charge, if you know about pre-charge or don't know about pre-charge, it's a very a thing which happens in very beginning of the vehicle, starting of the vehicle, that the capacitors in the motor controllers get charged suddenly because they have lowest resistance. We are talking about farads of sized capacitors, and it means that there are a lot of current within a short time. We call it as an inrush current. And then when we do that, actually the cell is not rated to give that much of current, and then even the conductors are not maybe rated. It means like you draw too much of current, you're going to affect the cell's life, or even the other component going to be go bad, and then the next thing is throw the battery and put the new battery, and that's the money. So we have certain pre-charge contactors that is controlled by BMS. We have isolation monitoring. At some cases, if the battery positive or battery negative, skinned out or some rat bite and it touches the ground, and then you have a potential hazard. You keep monitoring the isolation systems and then check if there is a leakage current, and then you'd also cut off the battery pack. Now, I know, because this is a 2-day course to describe for 16 hours or like 14 hours, and then understand how each functionality is predicted. But if you know overall, there is so much to ensure that there is a protection for the cell, right? And then the one side, and then the other side, the cell does certain measurements, and also cell does certain estimations depending upon the measured values of that cell. So like we measure voltage, we measure current, we measure temperature, we measure insulation. We also try to measure sometime impedance and predict an impedance in few cases. We estimate SOC. It means like amount of capacity left in the battery. SOH is like what is the health of the battery. It means like how much it can deliver at X amount of time. When the battery is going, charge control, like just not that much charger, just is led to charge the battery pack. Okay, so that's again controlled through the BMS. And then there's something called cell balancing. It means like if the various number of cells are there, each cell will possibly have a varied voltages at a given point. We need to ensure that those cells are always balanced and having the same voltage. So we do that through passive balancing and active balancing. Fast charge contactors. If you want to do a fast charging specific methodology with which we do a fast charge contactors. Discharge control, like the thermal control through a fan turning on or a pump turning. That's between your interface of the dashboard. Then and attention. like this, which is may not be like I would be able to mention. But if you understand, right, objective of an engineer who is an embedded engineer to write the codes is how do I put all these functionalities in a form of a code, 1,000 code inside the controller to see how actually the cell can be protected, and you can measure certain, and you can predict what what cell is going to behave in many different ways. The objective of a simulation code is to actually, the BMS code is to ensure, to consider all these parameters, embedded code, and that can work inside the controller in a fashion that the cell is always kept safer. So there are some protection logics. Because if I go to values, don't go by this value exactly. So let's say a flagging error condition. Cell voltage is greater than over voltage limit. Like this is the algorithm approach, how we write logical algorithms, like I would say even state machines. So if you talk about a voltage, like there's an over voltage limit, there's an under voltage limit. Right? Let's talk about it and how we actually define it. If the voltage is like a over voltage, okay, then it is because of the overcharging. It may be because derating error or a charger defect. That would be the two. Why overcharging is possible? Why possibly the cell is going above the voltage? Then reduce or stop the process, or even to a case you discharge the battery to bring back voltages within its. And then wait until we reach 4.2, or we don't wait until we reach 2.5, something like that, right? We have a very specific methodology. We call it as like MOL, maximum operating limit, rated like things like that, and then we also have MSO, very specific like state of the system at which we actually keep observing the system behavior at a cell voltages at a very specific point. Like the BMS is constantly measuring at a first point, and then the second point, third point. Like first is like MSO, then RSO, and then the MOL. So when we hit MOL, it means like the system is at error level. Okay, so you understand, right? So when a customer is driving the vehicle, imagine if you find a condition of RSO. It doesn't mean that you're just going to cut off the battery pack. You need to inform the customer. You need to bring up the warning to the customer that it's something wrong with the battery pack. Stop or pull down the car to the side of the vehicle. So the state conditions through which we write codes. So the things like that for the under voltage also. Like if you're doing the under voltage, it means like you're discharging the battery, right? Derating error or high standby or leakage current. Reduce or stop the discharge current, and then the charge the battery. Okay, the solutions of two, and possibly like set a flag at a specific value, set a flag of violation, of MSO. So this is the error states. Depending upon these error states, tell to our BMS what to do, right? But the way we report first, the report also there are very structured. Then those structural reports will actually take actions within the control logic, and those actions will be actually cut off the battery pack, or even to the warning to the customer that don't drive the vehicle, pull down the vehicle to the side roads, something like that, right? So then in further on, we have some more things, which is on the sides here. Just some inputs that the voice is going bad. Is it something that you all have an issue? Just let me know if you have issues of audio. So then, okay. So I'm sorry on that. Maybe it's just the internet connectivity. Sometimes just those bunkers. Okay, is it better now? The audio is okay. It's still the issue. You all have audio issues that you can't hear me properly. So we'll continue. I'll try to do what best I can do. The same way current protection logics, which is demonstrated. Charged current, like if the cell current is going above the limits, that's possibly a maximum charge current. So there are functionalities which is mentioned here on the screen, like when to set the flags and stuff like that, or maybe on the lower side, because on the current we don't usually talk about lower side because lower side is completely okay for the cell, but only the problem is in the higher side, right? It's only when when you draw a current to the cell more than the specific limits. So I just just show you the slides because it's self-explanatory and kind of gives you an understanding. How do we actually protect a cell from temperature? We have like cell temperature is greater than over temperature limits. The reasons possibly is like you're trying to draw a lot of current, or you possibly ambient temperature itself has gone high, or a case that the cooling the cooling system is faulty, right? So what we do, we reduce or stop the charge current, or we increase the cooling. And see, this state is only when the cell is getting charged, right? So when the cell temperature goes higher than the over temperature limits during discharge, so current is too high, it means you're drawing too much of current. Ambient temperatures are too high, but maybe the same thing, the cooling is defective. Reduce or stop the discharge current or increase the cooling systems. So like this, we have a specific state errors at that which we just kind of define and what to do, what not to do in your place. So similarly for pack level currents, for people who are wanting to be BMS engineers or BMS algorithm engineers, there's state error states or the state flagging or state machines are very, very important in your place. So let's talk about one more small thing here, which is on at the level of pack current. The pack current, the current is greater than a pre-charge current limit. What is the meaning of it? If the pre-charge current limit is crossed, it means there is possibly a faulty resistor which is used in the pre-charge circuit itself, or possibly there is a short circuit systems and things like that. It is straight away warning error, and you should cut off the system because if there is a pre-charge error into your place, yeah. So it means like you're constantly monitoring the system. Now the whole idea is actually to kind of brief out what we can do. These are the state logics, right? Now, similar to that, we have contactor feedback, like how the state machines I have defined before. There's something on contactor feedback. Imagine, I believe you know contactors. If you haven't take up the older courses, we're trying to brief them out. So like on and off of contactors. If the contactors was always on, then it's a very bad thing. We get a feedback from contactors. If there's a loss of communication, if the slave communication is lost, if it's open wire check, MCU die temperature, plausibility check, like this, we have a algorithm state machines. Okay. So then we would just run through a quick demonstration of the model itself, which we promised in the course content. But until now, what I covered is like why we perform simulation, how the logic of simulations is embedded into our place. We will run through the simulation, the model we have built, which kinds of I know, because again, building a simulation itself is like close to 8 hours to 12 hours of work. So I know it's not something easily possible to showcase everything within a few minutes what we have. So I'll just run you through one of the state cases that you could definitely get an idea of it at least, and then it brings you a motivation to work on further models, right? So hi Shravan, I'll bring our engineer. We build the models in partnership with certain racing teams and also in collaboration with other organizations. So I would bring in one of our race team engineers to showcase the model which we have collaboratively built. Shravan, you there?
Yes, sir.
Awesome. So I will, could you please, I'll stop sharing the screen. Yeah. So could you please share your screen and we could see the, okay, so we will be switching our screen to a screen on MATLAB. I believe it will be visible for all of you to kind of showcase that what we're trying to do here. Okay, interesting. Yeah, it's all visible now. I think it's all good for you. You can also see that the whole model into a place. So there are a few things here at a very overview point of it. I'll just write down some stuff on here to see you understanding. Yeah. So here on this part, you could see here, these are the flag machines. And this is a very fundamental one because definitely we can't also show the completely IP based the model, but definitely it is something at a functional level. It's working, and then you can see the results also. So this is a dashboard which gives us a flag that what is it overcharging and overcurrent, what's the over temperature during discharging conditions and stuff like that. I'll show you right, like on the error logic reporting stuff like that. We have a indicator stuff. We have certain parameter for the temperature, and we have some results blocks here. And inside this model, inside this place, we have built in the whole logic of the cell and the BMS itself. Okay, so yeah, so we'll open up the block on the cell, the BMS, the logic itself. So if you see here, we have two states. One is the charging state, other one is a discharging state. Okay, so as we discussed, like there are two conditions, right? One is a charging condition, discharging condition. Because over voltage can happen in charging, under voltage can happen in discharging. So it has to be a two separate sort of separations to identify the state cases. So once we have this, like we'll be able to demonstrate on the one other part. It will be the voltage side of the BMS, right? So we have a discharge of the cell model. We can open the discharge part of the cell model. If you see here, there's a whole lot of logic, which is also inbuilt in the whole model itself. So one of the overview we'll run you through be the OCV, that's an open circuit voltage, and how we're trying to predict an open circuit voltage itself. So for the predict open circuit voltage, we have two inputs. One is the current input, other one like basically the discharge current input and the cell temperature input. So we're trying to predict the open circuit voltage. It means the voltage of the cell at that given moment with respect to a temperature of the cell and the discharge current. So if I was trying to draw a small direction here, what we're trying to do is, let's take this line and two lines here. And imagine this is SOC versus voltage. So what really happens is if you take a line here, so we are trying to draw some discharge characteristics. I know this is not exact figure which will really come, but we're just trying to see, okay? So this characteristic is subjected to temperature of the cell, and this characteristic is also subjected to the rate of discharge. That means the current drawn from the cell, right? So it means this is a voltage graph, right? This is a voltage, and this is, let's say, you can call SOC or capacity of the cell, okay? Capacity of the cell. So there's a capacity of the cell in the y-axis, sorry, x-axis, and in the y-axis we have a voltage of the cell, right? So what we are trying to predict with one of the model we have built is we're trying to predict the voltage, which is here, which is a graph which is coming here. How much is the exact voltage with respect to the temperature of the cell and also the resistance, temperature of the cell and the rate of discharge of the cell. So those are the two inputs for us, but we need to predict a voltage, right? We are doing the same discussions, right, in the very beginning of our presentation, and the cell varily, shows out its voltage characteristics with respect to temperature and rate of discharge. So now, how we can actually model that? We have modeled it in a very way using certain graphs. Where there are many different models of trying to implement a specific approach of a model in doing it. So we have certain tables here, and we have certain tables here. Okay. We're trying to take the values of temperature and we're trying to feed into the specific table, which is there, which is the defined value, which we have got tested and got them filled inside the table. We're trying to feed the current. So if you're driving your race car, you can feed in the race car current graphs. How do you get these graphs? Actually, there is a approach of powertrain modeling. You can actually get those graphs. So we feed the graph. And some test cases, there is something called pulse discharge. We do feed the pulse discharge. We feed the current, we integrate it, then we do certain functionality here, then we get actually amps per second. But here we will convert into amps per hour. Using this table, we will get the capacity with respect to specific temperatures using this graph. And we feed in these values, and we know what is the state of the machine here, because we define like initial SOC is 100%. This is a input parameter which is here in this block. Then we know, depending upon the current which is being drawn out of the battery pack, like how much of the energy being taken out, it means the capacity is being taken out. We know the initial state of capacity. We know how much capacity we're going to draw from here in this condition. That capacity is also considered with respect to temperature as influence. Okay. So if the temperature is higher, it means the capacity of the cell will be lesser. It means the SOC predictions will be also, I would not say lesser. It means that comparatively an SOC at discharge of 25 degrees Celsius and SOC at 35 degrees Celsius is way too different comparatively, right? So which we get as an SOC output here, and also we will get as an OCV output here. The OCV is a open circuit voltage without load condition. Again, that is predicted through a specific Thule table, which we have got here. So the OCV is a functionality with respect to temperature. And again, the OCV is functionality with respect to SOC. So if you understand where we started with the current being input from the battery, then also temperature is being input to the model. With those inputs, we were able to predict how the capacity of the battery will vary with respect to temperature. And we fed that data. We were able to also get the current as a parameter. By inputting the current, by knowing the capacity with respect to the temperature, we are able to predict the exact SOC with respect to that temperature, right? So then we are able to feed that model into the other graph. We are able to predict the OCV, that's the open circuit voltage. And also that open circuit voltage is in consideration with respect to temperature of the cell, right? So it's like if you imagine like this is a way how models are built. If you want to go more complex, you can build a more complex model and then add some more parameters into it and try to see the accuracy of the model. But there is an always limitation. The more complex model you build, it becomes very challenging for the computation, and also it requires a lot of data as such itself. And the accuracy which you can get, you need to measure, so you can always know where the limits of complex you can build, and you can still have to get similar results. Rather than that, you could just limit yourself to a certain level and get the best values itself. This is a very approach of how actually like we build models and we get the values of SOC and OCV, and even SOC with respect to temperature, OCV with respect to temperature, OCV with respect to rate of discharge, and SOC with respect to rate of discharge, and things like that. Okay, this is one of the very simplistic visualizations. Shravan will go back. I believe this got you sort of an overview how we can predict, how we build the logic inside the BMS models. This is one of the things. Okay, it itself is a complex model, and it takes a lot of time to put everything into a structure. So now we can go back, Shravan. So this model contains the BMS logic and also the cell logic itself in together. We can open up the cell again. Sorry, the BMS logic itself, Shravan. So on the BMS logic, we're trying to sort of showcase one of the parameter, that is like how do we do under voltage protection, because it's a discharge part of the circuitry. We can set a specific parameter of voltage for the state of the requirements, and define if the cell is, because we're measuring the OCV, right, which you have seen in the last slide. It's an open circuit voltage actually. You can also get terminal voltages also by doing certain calculations and building the models. We get that voltage, then we feed that voltage, and now we know what is a voltage limit, like an under voltage limit. Each cell, by the data sheet, you can get to know what is under voltage limit. We will put that numbers into a place, and we will be able to predict. We can just move to the right, Shravan, and this can demonstrate on the smaller parts of it. Perfect. So we will feed the, yeah. So if you could see here on the way that, you could also define certain discharges. And we were discussing, right, that the battery BMS protects the cell by not allowing to go above and below certain voltages. Like there's under voltage protection and over voltage protection. Max discharge current, because this is a discharge set of it, we only have an under voltage set here. We have one more set which is for the over voltage, which is in the charging setup. So you can see here that we have set a max current and a max discharge current limit, max temperature, and a minimum discharge temperature. Like temperature, though, discharge can happen at lower temperatures, also higher temperatures also. We are defining a logic inside the BMS that, okay, you have to stop it here if the temperature is as like this. Because we're considering the ambient also, we are considering the cell internal temperatures also, using both of that. So this is a way we could put across the whole state machines. So I would say that the control logics, and then define whether the discharge need to be stopped here, whether the discharge need to be continued here, whether the discharge need to be limited here at a various different conditions. So then, yeah, that's pretty much onto the side of the model. And we can, Shravan, if we can run the model, is it, and kind of show the overall point of it.
Yeah.
Run the model. Yeah, please go ahead. To run the model, we have a current graph. Okay, we are feeding the current graph. How do we feed the current graph? We can feed a test graph, or we can also feed a drive cycle graph of the current. So we have a current profile. Of that profile, we are feeding into the model. And when we feed that current profile, and now the cell will be subjected to that current profile. Okay, so if I can just correlate you between this and realistic condition, you have to actually subject a cell with a test equipment. But here with a simulation, you can just set the profile and then feed that profile. It means like, it becomes quicker to study. Maybe what it takes to test a cell for 3 hours, because to charge a cell, to discharge a cell, possibly it will take like 5 hours or 4 hours. But here within like a fraction of few seconds, you can get a data, right? And that saves you a lot of time and things like that. So there would be some lag states. So this sort of gives you, an overview of how we could actually model things. Actually, this model consists of a cell model, and also this model consists of a BMS model too. So both of them kind of put together, and we could actually just run the model and predict the state of the system of over voltage and under voltage. Okay, so which you could also see here on the screen that how for a specific current profile there was no error situation. Like maybe there is no over voltage, overcharge, over temperature, or under voltage, over discharge current, discharge temperatures, and things like that. So this is like sort of a very fundamental way. If there is a case like in the current profile you're trying to feed, if you fed a very deep discharge currents, then possibly it will tell you over discharge currents. Then the flag will come up here, and then in the same way, now the flag will come here. It's sort of LED. But in real BMS, what will happen is, in the real BMS, we will actually stop. We'll send a signal to a contactor, and the contactor will open, or depending upon the situation, it will close. Then it will let the battery to charge or discharge for various conditions in turquoise. Cool. So that's in a very overview of actually conceptualizing everything from the theoretical point of it and actually building the simulation model itself. Okay. So this simulation model also, we have courses for cell modeling itself. We have a different course, and a BMS modeling also we have a different course that can be definitely planned across. And maybe I'll just brief you out to the last part of the discussions if you're interested. Thanks a lot, Shravan, for sharing the things into your place, and appreciate your time in sharing it.
Thank you, sir.
Thank you. So I'll go back to my presentation, and I just a few more things to share across from my side. I believe the session is kind of bringing you a realistic approach of how actually people develop algorithms. Now, I'll just give you an overrun on actually how algorithms are developed. Okay? So how actually the product development phases will be there in the real-time systems. Okay. So let's kind of, it's a recap of whole thing, what we have done till now. So there is something called model in the loop, then something called software in the loop, there's something called hardware in the loop. These are the three different steps every industry follows to develop algorithms for the BMS. Not only BMS, even motor controller, it may be even engine management system, body control system, HVAC system, any goddamn thing which is there in automotive will definitely go through the systematic approach of development. First is a model in the loop, second is software in the loop, the third is a hardware in the loop, right? So model in the loop is actually what we're trying to demonstrate to you. Okay, in the model in the loop, we will build a model within the simulation software. We will actually run the model for thousands of different conditions. We'll check whether the model is right, wrong, and stuff like that. The software in the loop, we will actually export that model to a C code, and then we will check if actually the software, which is a logic software, does work with respect to a targeted controller and things like that. Okay, so that's what is called the software in the loop. Then in the hardware in the loop, we will actually not have a real battery pack. Okay, so we will have a controller, which is like, if you want to know about a BMS, like there's a BMS controller, or there's a targeted hardware specifically. Then actually we will have a hill setup, hardware in the loop setup. And there's a companies like NI and there's a companies like SpeedGoat, and all these people provide these hardware supports. Like in that, what happens is your hardware HIL test bench will behave as a battery. Why do we use HIL? So imagine if you want to test the battery for 1,000 cycles, right? It would be such an amount of time, right? Because it will take enormous amount of time to charge, discharge, start, discharge. If you want to do a short circuit test, if you want to really perform a short circuit test on the real battery, you would possibly like make something go bad on the battery if the BMS is not functioning, BMS state functions are not functioning correctly. So it means that it's not possible to do all the tests in the real battery. So we have to perform certain tests without the battery itself. So, and also we do not have a battery pack when we're doing a product development stages, maybe sometimes. So that's why we use a HIO. So I'll run you through a few slides here, which kind of gives you a quick understanding. The cell modeling is the approach we have explained till now. Okay, we would build the models with different approaches, like a electrochemistry based or equivalent circuit based model, which is like you can just check through to read more on what exactly the equivalent circuit model is, how do you model, what are the parameters which we need to use when we're modeling the battery pack with the electrochemistry, RC based model, equivalent circuit based models. Then we could build the model to a simplicity and also to a complexity, like a 1 RC based or a 3 RC based. It is basically the representation of a real system within an electrical approaches. So that's what is like RCs are. So more the RC you keep, more complex the system becomes. We're trying to see more accuracy also with the higher RCs into our place. So we started at modeling through this approaches. Now we model the single cell here. That's what we did, right? Like we just modeled, this is a representation of a single cell model, okay? Then this is a representation of more number of cells, because in a battery pack, we have multiple number of cells. And also we need to include certain thermal behaviors. Now the cell level thermals were there. Now actually, because between two cells, there is a heat being generated. There is a transfer of heat. Then we can model all those things also in the pack level. Then this is possibly at a one module. Okay, the pack, I would mention this slide itself as a pack modeling with thermodynamics. We can mention here as a battery pack itself. Before it was a module, now it's a pack. It's like pack is a combination of multiple set of modules, right? It's a representation of the pack here. Now at the pack level, there are a lot of things like, there's a pack to pack contracts, there's a slave BMS sitting on the pack. A lot of these things will be there at a pack level. And then the last, like we put all the systems together. And then on the other side, we have interface of the charger, contactors, motor controllers, DC-DC converters, everything which comes in the powertrain systems, we can put them together. Then last comes the most important point, where actually, this is where we can run the model in a real-time condition. Okay, we can check how actually the model is going to behave by doing certain things that, we can build a plant model. Typically, we could call it a plant model or the vehicle model. So we can run the vehicle in a specific drive cycle. Okay. So imagine this is all happening virtually, right? So nothing is in realistic condition. Everything is happening virtually. So we take a vehicle, we run the vehicle in a specific format. We know the motor is going to operate in this RPMs, this torque levels, and all these things because of the acceleration. This is a value of velocity with respect to time. So we have built all the complex, resistive forces and things like that in here. I'm able to predict what is a motor torque, motor RPM. Because of the motor torque and motor RPM, motor torque, I get to know what is a motor current. Then for the RPM and the current, there's an inverter, which is basically the traction inverter, motor controller. We will be able to build a logic of the motor controller inside here, and then the converters if it is required in few cases in the battery pack itself. So until now, what we have built is only the battery pack. Okay, so we can subject the battery pack for this real-time test conditions within the laptop itself, within the simulation model itself. And then we could get to know how this battery is going to behave. Like imagine if I want to do that, I will repeat these cycles for 1,000 times. Then there's a charging, there's a discharging, there's a charging, and there's a discharging. At some time, the battery has reached certain percentage, there's a regenerative braking. We could be able to implement all of that into the battery and study how this battery is going to behave. Maybe what will be the resistance after the 100 cycle. Maybe what is the capacity of the battery after 100 cycle. Maybe what is a possibly the voltage depletions, like maybe even possibly what would be the number of cycles the battery has gone through. A lot of this parameter which we wanted to do a simulation studies, right? So that we can all perform. The best thing is this is all virtually. So we don't really need a vehicle. So by doing this simulation, before even purchasing a cell, before even purchasing a specific component, before even building a vehicle, we can predict how system is going to behave. And actually we can even configure the system sizes also, like what is the battery pack size, what is the motor size, what is the controller size, what is the controller efficiencies with respect to controller efficiencies, how the system is going to draw current with respect to motor operating points. We can do so much of things. And by the way, doing all of that, we could actually design the right battery management system. Okay, when we're running all these systems, we get to know how the cell is going to behave or the pack is going to behave. And depending upon that, we can define more control algorithms and we can predict the right SOC and things like that. So this is an overview of what we do. And when we perform all these things, this is a way. First, we start at a cell level. We expand ourselves to pack level simulations. Then we expand ourselves to system level simulations as such. Then this is the approach actually we do. There's something called as a HIL, which I was talking about. This is a host machine and stuff like that. Okay. And here through which we are able to feed all the drive cycle data and stuff like that. Here we have a target controller, which you could see here, right? This is a target controller. This is a Hill setup, hardware in the loop setup, which actually behaves as a battery, a real battery, like charging, discharging, temperature, like how the real battery behaves, the same way the HIL behaves. Now you have a target controller. You have the drive cycle, all the input parameters. Now the control logics are validated by performing the simulations. So you don't have a real battery, but we were able to develop algorithms by doing all this virtual system, virtual way of performing things. Then in the MATLAB, there is something called MATLAB Embed. So you could actually use that and export all your logic of this BMS control logics by validating that into a C code. And then you can put that C code into the BMS hardware itself. So this is a very standardized approach, how we actually perform and develop algorithms and how complex it is to develop this algorithm, because cell is a highly nonlinear system itself. So why we do all these things? Because if you see here that there is a very good clarity in terms of how things can go bad if you do not provide certain things rightly to the customer. If you could see here that Ather is promising a warranty of 3 years something, and after 3 years it will give you a 70% of the system performance. So this is from the Tesla Model X. Tells you can take 8 years, and they are promising 150,000 miles. I mean, that will be like miles is close 1.6, right? It's close around 2.25 lakhs, maybe nearly around 2.5 lakhs also, right? And they're promising 8 years of a cell life, right? And then they're able to promise that much of numbers. And then if you talk about Nissan Leaf here, give me a second here. One second. As far as there is a dependency on technology, there are problems. So yeah, so the thing is, like if you see Nissan Leaf here, the Nissan Leaf is predicting somewhere close to 96 months, or they're promising about 1 lakh kilometers, right? So if they're promising that, so if we understand from this perspective, one second, there are some connectivity issues. Okay, sorry about it. So coming back here, the screen is visible clearly. So If you see here that Nissan Leaf is promising 1 lakh kilometers, Ather is promising 3 years, then model Tesla is promising 1 lakh 50,000. They're also promising 1 lakh miles here, and they're promising 8 years with 1 lakh 20,000 miles. If you see all these things, if something goes wrong here with these timelines, they have to replace the battery pack, right? If they have to know confidently that the system will function, it means that you have to actually perform simulations and predict these models, because it is impossible to just promise something without testing that system. And testing the system for that many kilometers, it is not that very easily possible, right? That's when the logics of systems modeling will come. That is why modeling engineers are so much paid and so much valued in the industry for all the good reasons. So that's the end of the session on a whole coverage of the whole topics and things like that. I believe the session has brought you some level of understanding and some level of clarity on what exactly the modeling is, why we perform modeling for real-time conditions, why it is so important to model the simulations and stuff like that. And also on the technicality of all certain cells and the cell behavior and stuff like that, I believe we got an overall idea, and also the way industry develops the control algorithms and stuff like that. So with that, that's the end of the session. So I will take up QA sessions with a couple of slides ahead. So the certificates will be, for the people who have paid the fee, the certificates will be issued through the emails within 2 days going ahead. So why it's so important to get certificates? It gives you recognition. It's not about possibly just the information that you'll learn, to showcase across in the places like in LinkedIn, and to highlight yourself that you've undergone it. Because when somebody as a hiring person comes back and checks it out, what this guy has done. So it is just your posted things over there, and it kind of highlights you that I have been able to get worked out with this courses in this time, and this guy is interested to work on these things and stuff like that. So it's a part of recognition for somebody who would like to get it. So if somebody haven't actually taken as an opted as a part of certificates, we will share the links. So you could still account to take those certifications as a part of it if you're interested. There is no force in that. So Decibels also offers extensive, very in-depth approached courses, like than just running 3 hours, 2 hours, 4 hours courses. We have a day long for a complete 6 to 8 hours and up to 16 hours and week long courses in the advanced levels. So you could always take part in them. And when we attend a theory class, you get a concept of it, you get a idea of it. But actually, when you perform simulations, you get a deeper dive, and you get the system behaviors itself in a very, very in-depth manner. So we recommend you to take part in courses, and they're very affordable than any other available courses. And also they're very intuitive, and there's a trainer with you who teaches you live. And if you have a mistake and if you get stuck somewhere, trainers will help you. So there's a live doubt clarification, and you could model there. We can see your screen if you get stuck somewhere. We have courses on the vehicle modeling. We have courses on cell modeling. We have courses also upcoming on the motor controller modeling and the things like that. So which kind of gives you a very deeper exposure. And also you get respected a lot when you talk about technically when you want to get a job, and you talk realistically that this is how the system behaves with the knowledge of simulation. And definitely it's a need of the hour. I already explained to you how much it's important to perform simulation. So I believe that brings you an idea of why we take up our courses in the upcoming days. We'll share out the links, and also we'll share out certain coupon codes for people who have participated as a privileged participants. So you could apply them to also get some discounts. So so this is our website, lms.decibelslab.com. So you can always go there, check out our courses. So that's my email address, suraj@decibelslab.com. You could drop in the emails for any of the questions. On average, quite 100 emails, 50 emails we get every day. I would definitely respond back as quicker as possible with availability of resource and time, basically. If occupied, definitely one of my team member will reply back to you. So any questions and clarifications, you can always contact there, or you can always write as an email to contact@decibelslab or contact@decibelslab.com. So I believe this session has brought you the good idea and knowledge about things. Do share us your feedbacks here. That would be great for us to progress the sessions in the future. Your feedbacks are always valuable for us to take things into the future. So I believe we have made an honest effort to share our knowledge. We keep committing ourselves to share it for free for more and more people, to plan our courses as much as possible. If you felt good, do share it across to your friends and network of people. We would be always happy to connect back and make it more interactive, make it more worthwhile for all of you in the future and future too. Yeah. And so over at the ending note, before people leave, not for Q&A session, like more than like ourselves, the country needs engineers. The industry needs better and better engineers to build good electric vehicles. We've been the dumping ground for a lot of OEs from different countries to put their end-of-life vehicles to here. But I think to build that real vehicles, build that qualitative vehicles, to build that vehicles that really bring the change to electric mobility, we need engineers, because there's no university, I believe, have good courses itself, because we are industry struggling to get right engineers, but I'm sure it's not possible also that easily to get resources. So to train you, so we're there to train you, and over the training you, it doesn't matter if you take our courses, but India needs good engineers to bring better vehicles than importing Chinese and importing few components to in-house construct systems here. So guys like you who could definitely make things better and build an ecosystem, and companies like Aethers started out of the college today representing, better vehicles that represent the country in every place across. So you could also bring things, and you can at least be contributors in any of these technology developments. So with that, I end my note of discussions and delivering the course here. So if you have a part of the questions to ask, please do ask, and we'll be very happy to answer those questions. Okay, Ramakrishnan. So I would definitely try to put some PDFs into the LMS for the reference books and stuff like that. So by that, I would be able to end the technical delivery as a part of it. How do you know your lookup tables are always accurate and applicable to all the battery packs? Arush, it is not possible to tell that it is applicable for all the battery packs. For a specific cell, the BMS is designed for a specific, algorithms are designed for a specific cell. The BMS as a hardware can be used for anything, but the algorithms are specific to the specific cell. So you have to test the cell and get the values. Like, we don't have to do a rigorous lifetime testing, but you could test to a few cases. There are specific test algorithms and stuff like that. You can get those values. So we test the cell, we get the values, and then we perform a simulation to predict the future. That's the way it is. It is not for all the cells. It is for a specific cell. So if you have to do it for another cell, algorithm for another cell, you have to actually, get the data of that specific cell. From the basic science point of view, is it possible to simulate anode as well as cathode materials in the software? Can you simulate cyclic volumetric values? Ajay, yes, there are possibilities. Definitely, there are publications available. Do check them out. It is possible to predict that. People are doing it, like the tools like Cosmo, even in MATLAB also. The Cosmo is a very good software. People have been using it. Yeah, you could definitely use that. Could you please explain the 1D lookup table that gives the cell capacity as an output of the temperature? Okay, so I'll definitely try to write an answer, descriptive answer on that. If loads takes maximum 150, can I take 5 cells in parallel? Yes, Sumit, that's the approach of it. Yes. Thanks a lot, Sahil. Each with 20 max continuous current. Okay, will this be supported? See, there is something called nominal. There's something called peak. So you should know whether that 150 amps is peak because you define max. Max means peak. So you may not need 150 amps always, right? So you need nominal always. So it definitely depend upon that, approach of, maybe if I can go back to my very first slides of the presentation, I can give you some answers which is more clearistic. Yeah. So if you see here, on the side here that, yeah. So 150 is a peak, but your nominal is somewhere around like 40, 45 amps, 50 amps. So you have to know what is your nominal, what is your peak, depending upon the use size number of cells in parallel. So then, will this be supported? Great session. Also, will the SOC be affected for all batteries in parallel? Yeah, absolutely. Is this a 2-day course? No, I mean, like cell modeling itself is a 1 day and the BMS modeling is another day. So then that becomes 2 day. Surely, Pranab, I'll send an emails. I don't have like feedback forms right away. I'll send the feedback form through an email, so you guys can definitely reply back. Thanks a lot. Could you please brief me in a power fading once again? Okay, so power fading is like an approach. Let's say you want to accelerate a battery vehicle, right? So if you want to accelerate a vehicle, so you need a lot of power from the motor battery to be pumped out. So now if your battery has certain resistance, like the resistance increases over span, right? So then definitely because of the increased resistance, you won't be able to draw a lot of power at a given time. So because there's a cell reactions are not happening that faster for you to give out a lot of current, then by the way, you can't actually draw that power. That's what is called as a power fading. So you can accelerate as you could accelerate on the day one when you brought a vehicle. Akhil, certificates will be sent over to you through the email within 2 days. Yes, Sumir. Okay, what is RSL? So what is RSL? What is MSL? Those are the very abbreviations. So where we would define it for maximum safety limits. And MOL would be maximum operating limits and things like that. RSL, say SL is a safety limit. That's what a word is. R is an abbreviation. I quite forgot. I can just come back to you on that. Every battery creates SEI. Yeah, so that's for sure. And SEI is actually necessary for battery cell. It's good for the cell, but it is not being constant is a problem. If because it need to be formed to stop certain bad things to happen, but the problem is it is not constant. It will not be always there consistently in the same thickness. That's the problem. SEI is definitely good for the cells. The right amount of SEI is always good for the cells. So do we have classes again tomorrow at the same time, or are we done this with? So this is a 2-hour session. So this is done for today. So ongoing EV powertrain course, BMS model will be taught in detail. Yes, Zahim. So we will be covering up powertrain course. Not it's a internship which we have posted for 4 weeks and 6 weeks. People who are participating, yeah, we will help you out with building a BMS model. Yes. If cells are if cell parameters are so dynamic, how SOC is calculated at particular intent in real time? We do that by considering all the parameters, like how we're trying to do it, right? So the way we have done it. So it will be considering all these parameters, we will be able to predict it, like how the way you have seen, right? Like how we predict in voltage, open circuit voltage with temperature, with capacity and stuff like that. Sivaram Krishnan, yes. If you have registered in, I would say, pro internship category, The plus only until the vehicle modeling, but if you're registered in the Pro, yeah, we will do the modeling, yes. Is it possible to estimate SOH in simulation? Yes, Salil, it is possible. We are working on the algorithms, like Kalman filters we can use to predict SOH. Can you explain about a 1C graph? Okay. I mean, I didn't understand what you mean 1C graph explanation as such. All right, so maybe we'll take 2 more minutes here. It's 7:48, 7:50 would be the ending time. So if you have any questions, you have my contact number, so you could always be able to reach out to us. So, okay. I mean, what exactly you have a question? Do you have any specific questions, Sahil? Dhirendra, yeah, definitely. If you have logged into our LMS, lms.decibelslab.com, I believe still the course is available to enroll for free. If you have paid it, you already got an enrollment, I believe. You can enroll there. We'll try to add some references over there. I don't have something I can just type in here. Okay. So, Sahil, it means that simplicity. Okay. So, guys, maybe I know it's they definitely want to learn so many things, but time is a limitation. As such, maybe I don't have something like specific presentation which I could just have here to show you visually, and writing down everything will be complex. So, I'll surely share it across to you. Something I can write it down. Maybe I can share it across some of the documents onto the LMS itself, so where you can just refer them and go more deeper and understand. So, Imran, as such, there is coupon for. Yeah, we'll share you the coupon for advanced classes if you would like to participate. We'll send you an email if you would like to participate. Yeah. Awesome. So by that, I would end the session for today. So I really appreciate all of you to take part in participating in this course. And thanks a lot being a great audience. Thanks a lot being very interactive over the session. And it's always been great to host in future too. Do spread about Decibels. Do spread if you liked about our courses and contents and the information which we've been trying to qualitatively share to the learning community. Yep. Thanks a lot. Have a great evening ahead, and stay safe. Keep learning and happy learning. Thanks a lot. Take care. Bye bye.